Good morning, everyone. Yesterday, we were discussing about limitations of web, which has led to the uh, blueprint for semantic web. So, what is semantic web? The inventor of World Wide Web, Tim Berners-Lee, and W3C consortium team worked to develop, extend, and standardize the web's markup language and tools. In addition, they are designing is the next generation web architecture, the semantic web. Currently, the objective of semantic web architecture is to provide a knowledge representation of linked data in order to allow machine processing on a global scale. This involves moving the web from a repository of data without logic to a level where it is possible to express through logic through knowledge representation system. The vision for the semantic web is to augment the existing web with resources more easily interpreted by programs and intelligent agents. A defining application for the semantic web will be more effective search capabilities. While today search engines index HTML pages to find many answers and cover a huge part of the web, they return many irrelevant pieces of information. There is no notion of correctness to such searches. The difficulty of semantic search is perhaps its most important limitation. With the current state of the web, there are two methods of gaining broader information about documents. The first is to use a directory, a portal, or portal site manually constructed by searching the web and then categorizing pages and links. The problem with this approach is that directories take a tremendous effort to maintain. Finding new links, updating old ones, and maintaining the database technology all add to the portal's administrative burden and operating costs. The second method used automatic web crawling and indexing system. Consequently, searching the World Wide Web can be frustrating. The result of having better standard metadata could be a web where users and agents could directly tap the latent information in linked and related pages. This would be a powerful paradigm, greatly improving the intelligent use of web resources. By contrast, logic engines have typically been able to restrict their output to that which is probably correct answer, but have suffered from the inability to go through the mass of connected data across web to construct valid answer. If an engine if an engine of the future combines a reasoning engine with a search engine, it may actually be able to produce useful results. It will be able to reach out to indexes that contain very complete list of all occurrences of a given item and then use logic to weed out all but those that can be of use in solving the given problem. If the semantic web can bring structure and meaningful content to the web, it will create an environment where software agents can carry out sophisticated tasks for users. The first steps in weaving the semantic web with the existing web are already underway. In the near future, these developments will provide new functionalities as machines become better able to understand and process the data. For the semantic web to function, computers must have access to structured collection of information and sets of inference rules that they can use to conduct automated reasoning. Artificial intelligence researchers have long studied such systems and have produced today's knowledge representation. Knowledge representation is currently in a state comparable to that of hypertext before the advent of web. The objective of the semantic web, therefore, is to provide a framework that expresses both data and rules for reasoning for web-based knowledge representation. Adding logic to the web means using rules to make inferences, choose courses of action, and answering questions. A combination of mathematical and engineering issues complicates this task. The logic must be powerful enough to describe complex properties of objects, but not so powerful that agents can be tricked by being asked to consider a paradox. The development of the semantic web is proceeding in a step-by-step approach, building one layer on top of another. Two important technologies for developing the semantic web are already in place: XML and the resource description framework. Building one layer upon another requires each layer to have downward compatibility and upward partial understanding. Downward compatibility means the agents are fully aware of a layer to interpret and use information written at lower level. Upward partial understanding means the agents take at least partial advantage of information at higher levels. For example, an agent aware of RDF and RDF schemas semantics can interpret knowledge written in OWL by disregarding all but RDF and RDF schema elements. Extensible markup language lets everyone create their own tags, scripts, or programs can make use of these tags in sophisticated ways. But the script writer has to know how the page writer uses each tag. In short, XML allows users to add arbitrary structure to their documents, but says nothing about what the structure means. Why is XML important? So important. Just as HTML is an open standard that allows the information exchange and display over the internet, XML is not open standard that allows data to be exchanged between applications over the web. XML is the bridge to exchange data between the two main software development frameworks over the web, Java and J2EE and .NET. We can consider XML as a highly functional subset of HTML, but as a result, it is a meta language that allows users to design their own markup language. Three important technologies for developing the semantic web are resource development framework. Resource development framework contains the concept of an assertion and allows assertions about assertions. Meta assertions make it possible to rudimentary checks on document. Okay, we shall see this in the next module. RDF is a model of statements made about resources and associated URI. Its statements have a uniform structure of three parts: subject, predicate, and object. For example, the book subject, which is a subject, has the title, predicate, and author, object. With RDF, we can express statements in a formal way that software agents can read and act on. It lets us express a collection of statements as a graph, as a series of object, as a series of subject, predicate, object triples, or even in XML form. The first form is the most convenient for communication between people. The second for efficient processing, and the third for flexible communication with agent software. The next step of the language pyramid of web markup language, which address ontology and services languages, are web ontology language or OWL, semantic web rule language SWRL, and OWL services. So, what is ontology? An ontology is an agreement between agents that exchange information. The agreement is a model for structuring and interpreting exchanged data and a vocabulary that constrains these exchanges. Using ontology, agents can exchange vast quantities of data and consistently interpret it. Furthermore, they can infer new information by applying the ontology logical rules. A non-trivial ontology will allow logical inconsistencies, and as Gödel pointed out in his incompleteness theorem, in any axiomatic system, it is possible to create propositions that cannot be proved or disproved. This doesn't negate the usefulness of ontologies. However, it does mean ontologies, like everything else, have their limitations. In the AI community, the ability to infer new information from existing data is of fundamental importance, and this is sometimes misinterpreted as a defining feature of ontology. In fact, many ontologies only weakly support this capability. Ontology is also sometimes narrowly defined to mean hierarchical taxonomies or constrained vocabularies, but ontology may also contain assertions about how data can be structured and interpreted. The leading ontology system using RDF is Web Ontology Language called OWL. Uh, Web Ontology Language allows us formally express ontologies. The RDF provides some classification and rules, but OWL goes much further. In fact, one way to look at OWL is as the business rules for the semantic web. It is much more flexible than most business rule languages. Web Ontology Language. In 2003, the W3C began final unification of the disparate ontology efforts into a standardizing ontology and called it as OWL. This language is a vocabulary extension of RDF and is currently evolving into the semantic markup language for publishing and sharing ontologies on the World Wide Web. Web Ontology language facilitates greater machine readability of web content than the supported by XML, RDF, and RDFS by providing additional vocabulary along with formal semantics. It comes in several flavors as three increasingly expressive sublanguages: OWL Lite, OWL DL, and OWL Full. By offering these three flavors, OWL hopes to attract a broad following. Okay, and again, all these three things we'll study in the next module. So, what is ontology and their role in semantic web? Ontology-based knowledge representation. Ontology and the ontology languages may be viewed as one of the important technology in semantic web. Ontology can be described as formal allotment of conceptualization band to domain. This implies it provides the description of concepts and their corresponding relationship. In particular, the ontologies are designed as domain models that broadly appease or satisfy two special characteristics signifying the semantic webs. They are first one is ontologies are expressed in formal language with a well-defined semantics. The first point underlines the ontology. That ontology needs to be modeled using languages with a formal semantics such as languages include RDF and OW. These languages are treated as most frequently used languages in semantic web. These languages contain those models which are preferred by term ontology. Ontologies build upon a shared understanding within community. This understanding represents an agreement among members of the community over the concepts and relationships that are present in domain and their usage. RDF and OWL, the ontology languages, have standardized syntaxes and logic-based formal semantics. RDF and OWL are the languages most commonly used on semantic web. And in fact, when using the term ontology, many practitioners refer to domain models described in one of these two languages. The second point reminds us that there is no such thing as a personal ontology. For example, the schema of a database or UML class diagram that we created for the design of our own application is not an ontology. It is a conceptual model of a domain, but it is not shared. There is no commitment towards this schema for anyone else but us. The simplest structures are glossaries or controlled vocabularies, in essence, an agreement on the meaning of a set of terms. Semantic networks are essentially graphs that show how terms are related to each other. Thesauri are richer structures in that they describe a hierarchy between concepts and typically also allow describing related terms and alias. Thesauri are also the simplest structures where logic-based reasoning can be applied. The broader, narrow relationship of these hierarchies are transitive, in that an item that belongs to a narrow category also belongs to a direct parent and all of the ancestors. Taxonomy structures are regarded as weaker models that do not contain any explicit hierarchy, often comprise extra corresponding to the social context of tags. That is, the set of users who have been using this structure again success in extracting hierarchies and also relationship among the tags. The term lightweight ontology is typically applied to ontologies that make a distinction between classes, instances, and properties, but contain minimal description of them. On the other hand, heavyweight ontologies allow to describe more precisely how classes are composed of other classes and provide a richer set of constructs to construct how properties can be applied to classes. At the far end of the spectrum are complex knowledge bases that use the full expressivity of first order logic to define a great deal the kind of instances a concept may have and in which cases two instances may be related using a certain relationship. The more constrained the descriptions of concepts are, the less likely that their meaning will be misinterpreted by human readers. Ontologies can be organized according to complexity, as seen in the diagram. This is the informal level of semantics. In practice, the most web ontologies are all lightweight ontologies due to the need of serving the needs of many applications with divergent goals. Widely shared web ontologies also tend to be small as they contain only the terms that are agreed on by a broad user base. Large heavyweight ontologies are more commonly found in targeted expert systems used in focused domains with a tradition of formalized process and vocabulary such as the area of life science and engineering. So, ontology languages for the semantic web. We introduced the two ontology languages which have been standardized in recent years by the World Wide Web Consortium, RDF and OWL. So first we shall see RDF in detail and then we shall go to OWL. RDF means Resource Description Framework, or it is also called as RDF schema. The Resource Description Framework was originally created to describe resources on the World Wide Web. In reality, RDF is domain independent and, and can be used to model both real-world objects and information resources. RDF itself is a very primitive modeling language, but it is the basis of more complex language such as OWL. Before we see, just let's see some basics of HTML and XML. In 1990, when Tim Berners-Lee laid the foundation for the World Wide Web, he included three primary components: HTTP, URLs, and HTML. These three components represented the essential ingredients leading to the explosive growth of the World Wide Web. The original idea behind HTML was a modest one. Browsers such as Internet Explorer or Netscape Navigator could view information on web pages written in HTML. The HTML program can be written to the simple text file that is recognized by a browser application and can also be embedded script programming. As a result, it was so easy that it could be mastered by a high school student in a day. The following listing of HTML markup tags in the HTML. Okay, hello world example consisting of two tags, that is HTML head tags, that is head, and body tags, okay, that is body, with the displayed information weighed in between the appropriate tags. As the web flourished and the use of HTML became widespread, the limitations of the language began to foil continued progress. As more content moved to the web, those creating browsers realized that this simple markup language needed more capability. In particular, web applications such as web services required a means to explicitly manipulate data. This motivated to the development of XML. XML language. The HTML program is not extensible. That is, it has specifically designed tags that require universal agreement before changes can be made. Although over the years, Microsoft was able to add tags that work only in Internet Explorer, and Netscape was able to add tags that work only in Navigator. Website developers had no way of adding their own tags. The solution was XML, proposed in late 1996 by W3C. It offered developers a way to identify and manipulate their own structured data. The XML document simplified the process of defining and using metadata. The very nature of XML is that of a structured document representing the information to be exchanged, as well as metadata encapsulating its meaning. As a result, XML provides a good representation of extensible, hierarchical, and formatted information, and its required encoded metadata. XML is not a replacement, but rather a complementary technology to HTML. While XML is already widely used across the web today, it is still a relatively new technology. The XML is a meta language, which means it is a language used to create other languages. It can provide a basic structure and set of rules for developing other markup languages. By using XML, it is possible to create a unique markup language to model just about any kind of information. Markup text in general needs to be differentiated from the rest of document text by delimiters. Just as in HTML, the angle brackets and the names they enclose are delimiters called tags. Tags demarcate and label the parts of the document and add other information that helps define the structure. The XML documents lets you name the tags anything you want, unlike HTML, which limits you to predefined tag names. You can also choose element names that make sense in the context of the document. Tag names are case sensitive, although either case may be used as long as the opening and closing tag names are consistent. The text between the tags is the content of the document. Raw information that may be the body of the message a title or a field of data. The markup and the content complement each other, creating an information entity with partitioned labeled data in a handy package. The top, in its simplest form, an XML document is comprised of one or more named elements organized into a nested hierarchy. An element consists of an open tag, some data, and a closing tag. For any given element, the name of an opening tag must match that of the closing tag. A closing tag is identical to the opening tag except that less than symbol is immediately followed by a forward slash. Keeping this simple, we cannot construct the major portions of the XML document. The following six ingredients: XML declaration, document type definition, that is XML schema, elements required, attributes, entity, and notation. The top of an XML document contains special information called the document prologue. At its simplest, the prologue merely says that this is an XML document and declares the version of XML being used. The XML declaration is an announcement to the XML processor that this document is marked up in XML. That a declaration begins with the 5-character delimiter, that is less than $XML, followed by some number of property definitions, each of which has a property name and value in quotes. The declaration ends with 2-character closing delimiter, which you can see here. Okay, beginning and end. The document type definition DTD is used for validating the XML document. A DTD is a collection of parameters that describe a document type and include specific information about the sequence, frequency, and hierarchy of the XML documents, elements, attributes, and character data. The beginning of an XML document starts with the prologue that can hold additional information that nails down such details as the DTD being used. Declaration of special pieces of text, the text encoding and instructions to XML processor. The example of a well-defined XML declaration is here. Okay. The following the XML declaration is a document type declaration that links to DTD in a separate file. This is followed by a set of declarations. These parts together comprise the prologue. A simple XML hello world example is below. Okay, you can see this example here. The text between the tags message is the hello world text. In addition, XML is both a powerful and essential language for web services. It is the open standard that allows data to be exchanged between applications and databases over the web. As such, XML is the interoperable bridge for exchanging data between Java and Windows frameworks that support today's web services. Yet, despite the recognition of XML's importance today, it does not offer the semantics and logic capabilities. The next step up the markup language pyramid is RDF, which begins to establish a basis for the semantics on the web. So in the next class, we shall see about RDF. This is about basics of HTML and XML, which has led to the foundation of RDF. Okay, all of you mark your attendance. We shall continue about the RDF in the next class. Thank you.